Hey you guys, what's up? Hari ini aku coba pengen nonton lecture math. Ada 6 lecture, semoga bisa terkejar malam ini sampai jam 9:30. Okay, let's start.
X was minus 1 over x squared, and we also computed the derivative of x to the nth power for n equals 1, 2, etc. And that turned out to be n x to the n minus 1. So that's what we did last time. And today, I want to finish up with other points of view on what a derivative is. So this is extremely important. It's almost the most important thing I'll be saying in the class, but you'll have to think about it again when you start over and start using calculus in the real world. So again, we're talking about what is a derivative. And this is just a continuation of last time. So as I said last time, we talked about geometric interpretations, and today what we're going to talk about is rate of change as an interpretation of the derivative. So remember, we drew graphic functions, y equals fx, and we kept track of the change in x and here the change in y, let's say. And then, from this new point of view, a rate of change, keeping track of the rate of change of x and the rate of change of y, it's the relative rate of change we're interested in, and that's delta y over delta x. And it has another interpretation. This is the average change. And usually we would think of that if x were measuring time, and so the average, and that's when this becomes a rate. And the average is over the time interval delta x. And then the limiting value is denoted dy dx. And that is so this one is the average rate of change, and this one is the instantaneous rate. Okay, so that's the point of view that I'd like to discuss now. I'll give you just a couple of examples. So let's see. Well, first of all, so maybe some examples from physics here. So Q is usually the name for a charge, and then dq dt is what's known as current. So that's one physical example. A second example, which is probably the most tangible one, is we could denote the letter s by distance, and then the rate of change is what we call speed. So those are the two typical examples, and I want to illustrate the second example in a little bit more detail, because I think it's important to have some visceral sense of this notion of instantaneous speed. And I get to use the example of this very building to do that. Probably you know, or maybe you don't, that on Halloween there's an event that takes place in this building, or really from the top of this building, which is called the pumpkin drop. So let's illustrate this idea of rate of change with the pumpkin drop. So what happens is this building, well, let's see, here's the building. And here's the dot, that's the beautiful grass out on this side of the building, okay? And then there's some people up here and very small objects. Well, they're not that small when you're close to them. They get dumped over the side there, and they fall down. That's, everything at MIT, or a lot of things at MIT, are physics experiments. So that's the pumpkin drop. So roughly speaking, actually, the building's about 300 feet high. We're down here on the first usable floor. And so we're going to use, instead of 300 feet, just for convenience purposes, we'll use 80 meters, because that makes the numbers come out simply. Okay, so we have the height, which starts out at 80 meters at time 0, and then the acceleration due to gravity gives you this formula for h. This is the height. So at time t equals 0, we're up at the top. H is 80 meters. So this is the unit of meters. And at time t equals 4, you notice 5 times 4 squared is 80. So I picked these numbers conveniently so that we're down at the bottom. Okay, so this notion of average change here, so the average change, or the average speed here, maybe we'll call it the average speed, since that's over this time that it takes for the pumpkin to drop, is going to be the change in h divided by the change in t, which is, it starts out at, what does it start out as? It starts out as 80, right? And it ends at 0. So actually we have to do it backwards. We have to take 0 minus 80, because the first value is the final position, and the second value is the initial position, and that's divided by 4 minus 0, time 4 seconds minus time 0 seconds. And so that, of course, is minus 20 meters per second. So the average speed of this guy is 20 meters a second. Now, so why did I pick this example? Because, of course, the average, although interesting, is not really what anybody cares about who actually goes to the event. All we really care about is the instantaneous speed when it hits the pavement. And so that can be calculated at the bottom. So what's the instantaneous speed? That's the derivative. Or maybe I should, to be consistent with the notation I've been using so far, that's d by dt of h, right? So that's d by dt of h. Now remember, we have formulas for these things. We can differentiate this function now. We did that yesterday. So we're going to take the rate of change. If you take a look at it, it's just the rate of change of 80 is 0. minus the rate of change for this minus 5t squared, that's minus 10t. All right? So that's using the fact that d by dt of 80 is equal to 0. Case there, but the case n equals 0 also works. Right? Because that's constant, the derivative of constant is 0, and then the factor n there is 0, and that's consistent. And actually, if you look at the formula above it, you'll see that it's the case n equals minus 1. So we'll get a larger pattern soon enough with the powers. Okay, anyway, back over here, we have our rate of change, and this is what it is. And at the bottom, at the point of impact, we have t is equal to 4, and so h prime, which is the derivative, is equal to minus 40 meters per second. So it's twice as fast as the average speed here. And if you need to convert that, that's about 90 miles an hour, which is why the police are there at midnight on Halloween to make sure you're all safe, and also why when you come, if you need, which is the derivative, is equal to minus change. And this is what it is n equals minus 1. Because I'm cheating here, but there's a special case. So that's using the fact that d by dt of 80 is equal to 0, and d by dt of t squared is equal to 2t. The special case, well, I'm cheating here, but there's a special case that's obvious. I didn't throw it in over here. The case n equals 2 is that second case there, but the case n equals 0 also works. Right? Because that's constant, the derivative of constant is 0, and then the factor n there is 0, and that's consistent. And actually, if you look at the formula above it, you'll see that it's a case. N equals minus 1. So we'll get a larger pattern. So powers. Okay, anyway, back over here, we have a rate of change, and this is what it is. And at the bottom, at the point of impact, we have t is equal to 4, and so h prime, which is the derivative, is equal to minus 40 meters per second. So it's twice as fast as the average speed here. And if you need to convert that, that's about 90 miles an hour, which is why the police are there at midnight on Halloween. Make sure you're all safe, and also why when you come, you have to be prepared to clean up afterwards. So anyway, that's what happens. It's 90 miles an hour. It's actually the building's a little tough. But there's air resistance. I'm sure you can do a much more thorough study of this example. All right, so now I want to give you a couple of more examples because time is, and these kinds of parameters and variables are not the only ones that are important for calculus. If it were only this kind of physics that was involved, then this would be a much more specialized subject than it is. And so I want to give you a couple of examples that don't involve time as a variable. So the third example I'll give here is the letter T often denotes temperature. And then dt dx would be what is known as the temperature gradient, which we really care about a lot when we're predicting the weather, because it's that temperature difference that causes airflows and causes things to change. And then there's another theme which is throughout the sciences and engineering, which I'm going to talk about under the heading of sensitivity of measurements. So let me explain this. I don't want to belabor it because I just am doing this in order to introduce you to the ideas on your problem set, which are the first case of this. So on problem set 1, you have an example which is based on a simplified model of GPS, sort of the flat Earth model. And in that situation, well, if the Earth is flat, it's just a horizontal line like this. And then you have a satellite, which is over here, preferably above the Earth. And the satellite knows exactly, or the system knows exactly where the point directly below the satellite is. So this point is treated as known. And I'm sitting here, okay, with my little GPS device, and I want to know where I am. And the way I locate where I am is I communicate with the satellite by radio signals, and I can measure this distance here, which is called h. And then the system will compute this horizontal distance, which is L. So in other words, what's measured, so h measured by radio waves in a clock, or various clocks, and then L is deduced from h. And what's critical in all of these systems is that you don't know h exactly. There's an error in h, which will denote delta h. There's some degree of uncertainty. The main uncertainty in GPS is from the ionosphere, but there are lots of corrections that are made of all kinds. And also, if you're inside a building, it's a problem to measure. But it's an extremely important issue, as I'll explain in a second. So the idea is we then get to the get at delta L is estimated by considering this ratio, delta L over delta h, which is going to be approximately the same as the derivative of L with respect to h. So this is a thing that's easy because, of course, it's calculus. Right? Calculus is the easy part, and that allows to deduce something about the real world that's close by over here. So the reason why you should care about this quite a bit It's used all the time to land airplanes. And so you really do care that they actually know to within a few feet or even closer where your plane is and how high up it is and so forth. All right. So that's it for the general introduction to what a derivative is. I'm sure you'll be getting used to this in a lot of different contexts throughout the course. And now we have to get back down to some rigorous details. Okay? Is everybody happy with what we got so far? Yeah? Good question. Question was, how did I get this equation for height? I just made it up because it's the formula from physics that you will learn when you take 801. And it has to do with the fact that in fact, it has to do with the fact that if you, this is speed, if you differentiate another time, you get acceleration, and this is the acceleration due to gravity is 10 meters per second, which happens to be the second derivative of this. But anyway, I just pulled it out of a hat from your physics class. So you can just say C801. All right, other questions? All right, so let's go on now. Now, I have to be a little bit more systematic about limits. And so let's do that now. So now what I'd like to talk about is limits and continuity. And this is a warm-up for deriving all the rest of the formulas. All the rest of the formulas that I'm going to need to differentiate every function you know. Remember, that's our goal, and we only have about a week left, so we better get started. So first of all, there's what I will call easy limits. So what's an easy limit? An easy limit is something like a limit x equals 4. Because, so what I get here is 4 plus 3 divided by 4 squared plus 1. And that's just 7 divided by 17. And that's the end of it. So those are the easy limits. The second kind of limit, well, so this isn't the only second kind of limit, but I just want to point this out, it's very important, is that derivatives are always harder than this. You can't get away with nothing here. So why is that? Well, when you take a derivative, you're taking a limit as x goes to x0 of f of x, well, f of x, let's try, we'll write it all out in all its glory. Here's the formula for a derivative. Now notice that if you plug in x equals x0, always gives 0 over 0. So it just basically never works. So we always are going to need some cancellation to make sense out of the limit. Now, in order to make things a little easier for myself to explain what's going on with limits, I need to introduce just one more piece of notation. What I'm going to introduce here is what's known as a left-hand and a right-hand limit. If I take the limit as x tends to x0 with a plus sign here of some function, this is what's known as the right-hand limit. And I can display it visually. So what does this mean? It means practically the same thing as x tends to x0, except there's one more restriction which has to do with this plus sign, which is we're going from the plus side of x0. That means x is bigger than x0. And I say right hand, so there should be a hyphen here, right hand limit, because on a number line, if x0 is over here, the x is, the x is to the right. Right? So that's a right hand limit. And then this being the left side of the board, I'll put on the right side of the board the left limit, just to make this confusing. So that one has the minus sign here. I'm just a little dyslexic, and I hope you're not. So I may have gotten that wrong, but so this is on the other side of it. Okay, so those two notations are going to help us to clarify a bunch of things. It's much more convenient to have this extra bit of description of limits than to just consider limits from both sides. Okay, so I want to give an example of this. And also an example of how you're going to think about these sorts of problems. So I'll take a function which has two different definitions. Say it's x plus 1 when x is bigger than 0, and minus x plus 2 when x is less than 0. All right, so maybe put commas there. Those are so when x is greater than 0, it's x plus 1. Now I can draw a picture of this. It's going to be kind of a little small because I'm going to try to fit it down in here, but maybe I'll put the axis down below. So at height 1, I have to the right, I have something with slope 1, so it goes up like this. All right, and then to the left of 0, I have something which has slope -1. But it hits the axis at 2, so it's up here, right? So I have this sort of strange antenna figure here, which is my graph. Maybe I should draw these in another color to depict that, all right? And then if I calculate these two limits here, what I see is that the limit as x goes to 0 from above of f of x, that's this again, but now because I'm limits, and this is one little tiny subtlety, and it's almost the only thing that I need to really pay attention to a little bit right now, is that this, we did not need x equals 0 value. In fact, I never even told you what f of 0 was here. If we stick it in, we could stick it in, okay, let's say we stick it in on this side. Let's make it be that it's on this side. So that means that this point is in, and this point is out. So that's a typical notation, this little open circle and this closed dot for when you included the. So in that case, the value of f of x happens to be the same as its right-hand limit, namely the value is 1 here, and not 2. Okay, so that's the first kind of example question. Okay, so now our next job is to introduce the definition of continuity. So that was the other topic here. So we're going to define, so f is continuous at x0 means that the limit of f of x as x tends to x0 is equal to f of x0. So the reason why I spent all this time paying attention to the left and the right and so on and so forth, and focusing, is that I want you to pay attention for one moment to what the content of this definition. First one is that this limit exists. And what that means is that there's an honest limiting value both from the left and right. And they also have to be the same. All right, so that's what's going on here. And the second property is that f of x0 is defined. So I can't be in one of these situations where I haven't even specified what f of x0 is, and they're equal. Okay? So that's the situation. Now, again, let me emphasize a tricky part of the definition of a limit. This side, the left-hand side, is completely independent, is evaluated by a procedure which does not involve the right-hand side. These are separate things. This one is, to evaluate it, you always avoid the limit point. So that's, if you like, a paradox, because it's exactly the question is it true that if you plug in x0, you get the same answer as if you move in the limit? That's the issue, that we always avoid the limit point. So that's, if you like, a paradox, because it's exactly... The question is it true that if you plug in x0, you get the same answer as if you move in the limit? That's the issue that we're considering here. We have to make that distinction in order to say that these are two. Otherwise, it's just tautological. It's a very little, it doesn't have any meaning. But in fact, it does have meaning because one thing is evaluated separately with reference to all the other points, and the other is evaluated right at the point in question. And indeed, what these things are exactly the easy limits. Have to make a distinction, and these other ones are going to be the ones which we can't evaluate that way. So these are the nice ones, and that's why we care about them, why we have a whole definition associated with them. All right. So now what's next? Well, I need to give you a little tour, a very brief tour of the zoo of what are known as discontinuous functions. So sort of everything else that's not continuous. So the first example here, let me just write it down here, is jump discontinuities. So what would a jump discontinuity be? Well, we've actually already seen it. The jump discontinuity is the example that we had right there. This is when the limit from the left and right exist, but are not equal. Okay, so that's as in the example. Right, in this example, the two limits, one of them was 1, and one of them was 2. So that's a jump discontinuity. And this kind of issue of whether something is continuous or not is may seem a little bit technical, but it is true that that people have worried about it a lot. Bob Merton, who was a professor at MIT when he did his work for the Nobel Prize in economics, was interested in this very issue of whether stock prices of various kinds are continuous from the left or right in a certain model. And that was a very serious issue in developing a model that priced things that our hedge funds use all the time now. So left and right really can mean something very different. In this case, left is the past and right is the future. And it makes a big difference whether things are continuous from the left or continuous from the right. Right? Is it true that the point is here, somewhere in the middle, somewhere else? That's a serious issue. So the next example that I want to give you is a little bit more subtle. It's what's known as a removable discontinuity. And so what this means is that the limit from left and right are equal. So a picture of that would be you have a function which is coming along like this, and there's a hole maybe where, who knows, either the function is undefined or maybe it's defined up here, and then it just continues on. All right, so the two limits are the same. And then, of course, the function is begging to be redefined so that we remove that hole. And that's why it's called a removable discontinuity. Now let me give you an example of this, or actually a couple of examples. So these are quite important examples which we'll be working with in just a few minutes. So the first is the function g of x, which is sine x over x. And the second will be the function h of x, which is 1 minus cosine x over x. So we have a problem at g of 0. G of 0 is undefined. On the other hand, it turns out that this function has what's called a removable singularity, namely the limit as x goes to 0 of sine x over x does exist. In fact, it's equal to 1. So that's a very important limit that we'll work out either at the end of this lecture or at the beginning of next lecture. And similarly, the limit of 1 minus cosine x we need later on. And what they say is that these things have removable singularities. Sorry, removable discontinuity at x equals 0. All right, so as I said, we'll get to that in a few minutes. Okay, so are there any questions before I move on? Yeah? The question is, why is this true? Is that what your question is? The answer is, it's very, very unobvious. I haven't shown it to you yet. And if you were not surprised by it, then that would be very strange indeed. So we haven't done it yet. You have to stay tuned until we do, okay? We haven't shown it yet. And actually, even this other statement, which maybe seems stranger still, is also not yet explained. Okay, so we're going to get there, as I said, either at the end of this lecture or at the beginning of next. Other questions? All right, so let me just continue my tour of the zoo of discontinuities. And I guess I want to illustrate something with the convenience of right and left-hand limits. So I'll say this board about right and left-hand limits. So a third type of discontinuity is what's known as an infinite discontinuity. And we've already encountered one of these. I'm going to draw them over here. Remember, the function y is 1 over x. It's the graph of 1 over x. And the convenience here of the distinguishing the left and the right-hand limits is very important, because here I can write down that the limit as x goes to 0 plus 1 over x. Well, that is going down. You should write this. It's just that it's wrong. It's not that they don't write it down. In fact, you'll probably see it. It's the statement that the limit as x goes to 0, 1 over x is infinity is simply wrong. Okay? It's not that people don't write this. It's just that it's wrong. It's not that they don't write it down. In fact, you'll probably see it. It's because people are just thinking of the right-hand branch. It's not that they're making a mistake necessarily, but anyway, it's sloppy. And there's some sloppiness that we'll endure and others that we'll try to avoid. So here, you want to say this, and it does make a difference. Plus infinity is an infinite number of dollars, and minus infinity is an infinite amount of debt. They're actually different. They're not the same. So, this is sloppy, and this is actually more correct. Okay, so now, in addition, I just want to point out one more thing. Remember, we calculated the derivative, and that was minus 1 over x squared. But I want to draw the graph of that and make a few comments about it. So I'm going to draw the graph directly underneath the graph of the function. And notice what this graph is. It goes like this. It's always negative, and it points down. So now this may look a little strange, that the derivative of this thing is this guy, but that's because of something that's very important. You should always remember this about derivatives. The derivative of a function looks nothing like the function necessarily. So you should just forget about that as being an idea. Some people feel like if one thing goes down, the other thing has to go down. Just forget that. Intuition is wrong. What we're dealing with here, if you remember, is the slope. So if you have a slope here, that corresponds to just a place over here. And as the slope gets a little bit less steep, that's why we're approaching the horizontal axis. The number's getting a little smaller as we close in. Now over here, the slope is also negative. It's going down. And as we get down here, it's getting more and more negative. As we go here, the slope, this function is going up, but its slope is going down. All right, so the slope is down on both sides. And the notation that we use for that is well suited to this left and right business. Namely, the limit as x goes to 0 of negative 1 over x squared, that's going to be equal to minus infinity, and that applies to x going to 0 plus and x going to 0 minus. So both have this property. Finally, let me just make one last comment about these two graphs. This function here is an odd function. And when you take the derivative of an odd function, you always get an even function. And that's closely related to the fact that this 1 over x is an odd power, and this 2, x to the first power is an odd power, and x squared is an even power. So all of your intuition should be reinforcing the fact that these pictures look right. Okay, now there's one last kind of discontinuity that I want to mention briefly, which I will call other. Ugly discontinuities. And there are lots and lots of them. And so one example would be the function y is equal to sine 1 over x as x goes to 0. And that looks a little bit like this. Back and forth, back and forth. It oscillates infinitely often as we tend to 0. And there's no left or right limit in this case. So there's a very large quantity of things like that. Fortunately, we're not going to deal with them in this course. A lot of times in real life, there are things that oscillate as time goes to infinity, but we're not going to worry about that right now. Okay, so that's our final mention of the discontinuity. And now I need to do just one more piece of groundwork for our formulas next time. Namely, I want to check for you one basic fact, one limiting tool. So this is going to be a theorem. But fortunately, it's a very short theorem, and has a very short proof. So the theorem goes under the name differentiable implies continuous. And what it says is the following. It says that if f is differentiable, in other words, the derivative exists at x0, then f is continuous at x0. So we're going to need this as a tool, a key step in the product and quotient rules. So I'd like to prove it right now for you. So here's the proof. Fortunately, the proof is just one line. So first of all, I want to write in just the right way what it is that we have to check. So what we have to check is that the limit as x goes to x0 of f of x minus f of x0 is equal to 0. So this is what we want to know. We don't know it yet, but we're trying to check whether this is true or not. So that's the same as the statement that the function is continuous, because the limit of f of x is supposed to x 0. And so this difference should have limit 0. And now, the way this is proved is just by rewriting it, by multiplying and dividing by x minus x 0. So I'll rewrite the limit as x goes to x 0 of f of x minus f of x 0 divided by x minus x 0 times x minus x 0. Okay, so I wrote down the same expression that I had here. This is just the same limit, but I multiplied and divided by x minus x 0. And now, when I take the limit, and here, these are just the same limit of x minus f of x 0 divided by x minus x 0 times x minus x 0. Okay, so I wrote down the same expression that I had here. These are just the same limit, but I multiplied and divided by x minus x. And now, when I take the limit, what happens is the limit of the first factor is f prime of x 0. That's the thing we know exists by our assumption. And the limit of the second factor is 0. Because the limit is x goes to x 0, x minus x 0 is clearly 0. So that's it. The answer is 0, which is what we want. Right, so that's the proof. Now, there's something exceedingly fishy looking about this proof. And let me just point to it before we proceed. Namely, you're used in limits to setting x equal to 0. And this looks like we're multiplying dividing by 0, exactly the thing which makes all proofs wrong in all kinds of algebraic situations and so on and so forth. You've been taught that that never works, right? But somehow these limiting tricks have found a way around this. And let me just make explicit what it is. In this limit, we never are using x equals x 0. That's exactly the one value of x that we don't consider in this limit. That's how limits are cooked up. And that's sort of theme so far today is that we don't have to consider that. And so this multiplication and division by this number is illegal. It may be small, this number, but it's always non-zero. And so this really works, and it's really true, and we've just checked that a differentiable function is continuous. So I'm going to have to do these, carry out these limits, which are very interesting, 0 over 0 limits, next time. But let's hang on for 1 second to see if there are any questions before we... So, yeah, there is a question. I'll repeat this proof right here. Okay, just say again. Okay, so there are 2 steps to the proof, and the step that you're asking about is the first step, right? And what I'm saying is if you have a number, and you multiply it by 10 over 10, it's the same number. If you multiply it by 3 over 3, it's the same number, 2 over 2, 1 over 1. And we just checked that a differentiable function is continuous. So, carry out these limits, which are very interesting, 0 over 0. Proof right here. Okay, just say again. Okay, so there are 2 steps to the proof, and the step that you're asking about is the first step. Right? And what I'm saying is if you have a number and you multiply it by 10 over 10, same number. If you multiply it by 3 over 3, it's the same number. 2 over 2, 1 over 1, so on. So it's okay to change this to this. It's exactly the same thing. That's the first step. Yes?
Very simple.
The question was, how does this line, yeah, where the question mark is. So what I checked was that this number, which is on the left-hand side, is equal to this very long, complicated number, which is equal to this number, which is equal to this number, and so I checked that this number is equal to 0 because the last thing is 0. This is equal to that, is equal to that, is equal to 0. And that's the proof. Yes? Yeah, so that's a different question. Okay, so the hypothesis of differentiability I use because this limit is equal to this number, that limit exists. That's how I use the hypothesis of the theorem. The conclusion of the theorem is the same as this, because being continuous is the same as limit as x goes to x0 of f of x is equal to f of x0. That's the definition of continuity. And I subtracted f of x0 from both sides to get this as being the same thing. So this claim is continuity, and it's the same as this question here. Last question.
How do we get the 0 from x minus x0?
How do we get the 0 from this? So the claim that's being made, so the claim is why is this tending to that? So for example, I'm going to have to erase something to explain that. So the claim is that the limit as x goes to x0 of x minus x0 is equal to 0. That's what I'm claiming. Okay? Does that answer your question? Okay. All right. Ask me else. So the claim is that the limit as x goes to x0 of x minus x0 is equal to 0. That's what I'm claiming. Okay? Does that answer your question? Okay. All right. Ask me else other stuff after lecture.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
In today's lecture, I want to develop several more formulas that will allow us to reach our goal of differentiating everything. So these are derivative formulas. And they come in two flavors. The first kind is specific. So some specific function we're giving the derivative of, and that would be, for example, x to the n or 1 over x. Those are ones that we did a couple of lectures ago. And then there are general formulas. And the general ones don't actually give you a formula for a specific function, but tell you something like, if you take two functions and add them together, their derivative is the sum of the derivatives. Or if you multiply by a constant, for example. So c times u, the derivative of that is c times u prime, where c is constant. All right, so these kinds of formulas are very useful, both the specific and the general kind. For example, they're needed, so we need both kinds for polynomials. And more generally, pretty much any set of formulas that we give you will give you a few functions to start out with, and then you'll be able to generate lots more by these general formulas. So today, we want to concentrate on the trig functions, and so we'll start out with some specific formulas. And they're going to be the formulas for the derivative of the sine function and the cosine function. So that's what we'll spend the first part of the lecture on, and at the same time, I hope to get you very used to dealing with trig functions, although that's something that you should think of as a gradual process. All right, so in order to calculate these, I'm going to start over here and just start the calculation. So here we go. Let's check what happens with the sine function. So I take sine x plus delta x, I subtract sine x, and I divide by, sorry, let's leave a little space there, sine x and divide by delta x. All right, so this is the difference quotient, and eventually I'm going to have to take a limit as delta x goes to 0. And there's really only one thing we can do with this to simplify or change it, and that is to use the sum formula for the sine function. So that's this, that's sine x cosine delta x plus, oh, that's not what it is. Okay, so what is it? Sine x, sine delta x, okay, good, you remember. Plus cosine, no? Oh, okay, so which is it? Okay, all right, let's take a vote. Is it sine sine or is it sine cosine? Okay, so is this going to be cosine? All right, you better remember these formulas, all right? Okay, it turns out that it's sine. Okay, so is this going to be x sine delta x cosine delta x plus oh, that's what it is. Okay, so what is it? Sine x sine delta x. Okay, good, you remember. plus cosine. No? Oh, okay.
Sin, cos, cos.
Which is it? Okay. All right, let's take a vote. Is it sine, sine, or is it sine, cosine? Okay, so is this going to be cosine? All right. All right, you better remember these formulas, all right? Okay, it turns out that it's sine, cosine, right? Cosine, sine. So here we go. No, you got to do x here, sine, delta x. All right? So now, there's lots of places to get confused here. And you're going to need to make sure that you get it right, all right? So we're going to put those in parentheses here. Sine a plus b is sine a cos b plus cos a sine b. All right? Now that's what I did over here, except it was the letter x was a, and the letter b was delta x. All right? Now that's just the first part. That's just this part of the expression. All right, so now, the next thing we're going to do is we're going to try to group the terms. And the difficulty with all such arguments is the following one. Any tricky limit is basically 0 over 0 when you set delta x equals 0. If I set delta x equals 0, this is sine x minus sine x, so it's a 0 over 0 term. Here we have various things which are 0 and various things which are non-zero. We must group the terms so that a 0 stays over a 0. Otherwise, we're going to have no hope. If we get some 1 over 0 term, we'll get something meaningless in the limit. So I claim that the right thing to do here is to notice, I'll just point out this one thing, is that when delta x goes to 0, this cosine of 0 is 1. So it doesn't cancel unless we throw in this extra sign term here. So I'm going to use this common factor and combine those terms. So this is really the only thing that you're going to have to check. Particular calculation. So we have the common factor of sine x, and then that multiplies something that will cancel, which is cosine delta x minus 1 divided by delta x. So that's the first term. And now what's left? Well, there's a cosine x that factors out, and then the other factor is sine delta x over delta x. Okay, now, does anyone remember from last time what this thing goes to? How many people say 1? How many people say 0? All right, it's 0. That's my favorite number. All right, 0. It's the easiest number to deal with. So this goes to 0, and that's what happens as delta x tends to 0. Now, how about this one? This one goes to 1, my second favorite number. Almost as easy to deal with as 0. And these things are picked for a reason. They're the simplest numbers to deal with. So altogether, this thing, as delta x goes to 0, goes to what? I want a single person to answer. Great volunteer. All right, right back there. Cosine. Because this factor is 0, it cancels, and this factor has a 1, so it's cosine. So it's cosine x. All right, so our conclusion of 1, sine b. All right. So you'll have to be willing to call those forth at will right now. So, okay, so let's do the cosine now. So that's cosine x plus delta x minus cosine x divided by delta x. Okay, there's the difference quotient for the cosine function. And now I'm going to do the same thing I did before, except I'm going to apply the second rule, that is the sum rule for cosine. And that's going to give me cosine x, cosine delta x, minus sine x, sine delta x. And now you have to remember, again, to subtract cosine divided by this delta x. And now I'm going to regroup just the way I did before, and I get the common factor. For cosine, multiplying cosine delta x minus 1 divided by delta x. And here I get the sine x, but actually it's minus sine x. And then I have sine delta x divided by delta x. All right? The only difference is this minus sign, which I stuck aside. Well, that's not the only difference, but it's a crucial difference. Okay, again, by a, we get that this is 0, sine x. So we'll get ourselves started by mentioning that. Now, maybe before I do that, though, I want to show you how a and b fit into the proofs of these theorems. So let me just make some remarks here. So this is just a remark, but it's meant to help you. sine and cosine at x equals 0 give all values of d by dx sine x, d by dx cosine x. So that's really what this argument is showing us, is that we just need one rate of change at one place, and then we work out all the rest of them. Sense that we want to make sure, okay, so this kind of result. And that's because, and to write down a geometric proof, we're going to have to draw a picture. And the first step in the proof really is to replace this variable delta x, which is going to 0, with another name, which is suggestive of what we're going to do, which is the letter theta for an angle. Okay, so let's draw a picture of what it is that we're going to do. And here's the circle, and here is the origin, and here's some little angle. Well, I'll draw it a little larger so that it's visible. Here's theta, right? And this is the unit circle. I won't write that down on here, but that's the unit circle. And now sine theta is this vertical distance here. Maybe I'll draw it in a different color so you can see it all. Okay, so here's that down on here. That's the unit circle. And now sine theta is this vertical distance here. Maybe I'll draw it in a different color so you can see it all. Okay, so here's this distance. So this distance is sine theta. Okay? Now, almost the only other thing we have to write down in this picture to have it work out is that we have to recognize that when theta is the angle, that's also the arc length of this piece of the circle when measured in radians. So this length here is also arc length. Whoops, arc length theta. That little piece in there. So maybe I'll use a different color for that. Okay, so here's orange, and that's this little chunk there. Okay? So those are the two pieces. Now, in order to persuade you now that the limit is what it's supposed to be, I'm going to extend the picture just a little bit. I'm going to double it, just for my own linguistic sake, so that I can tell you a story, all right? So that you'll remember this. So I'm going to take a theta angle below, and I'll have another copy of sine theta down here. And now the total picture is really like a bow and its bowstring there, all right? So what we have here is a length of 2 sine theta, so maybe I'll write it this way. 2 sine theta, I just doubled it. And here I have underneath 2, whoops, I got it backwards. Sorry about that. I'm trying to be with the colored chalk, and I have it reversed. And here I have underneath 2, whoops, I got it backwards. Sorry about that. I'm trying to be fancy with the colored chalk, and I have it reversed here. So this is not 2 sine theta. 2 sine theta is the vertical, that's the green. So let's try that again. This is 2 sine theta, all right? And then in the denominator, I have the arc length, which is theta is the first half, and so double it is 2 theta, all right? So if you like, this is the bow, and up here, we have the bowstring. Right? And of course, we can cancel the 2's, that's equal to sine theta divided by theta. And so now why does this tend to 1? It goes to 0. Well, it's because as the angle gets very small, this curved piece looks more and more like a straight one. All right? And if you get very, very close here, the green segment and the orange segment would just merge. They would be practically on top of each other. And they have closer and closer and closer to the same length. So that's why this is true. I guess I'll articulate that by saying that short curves are nearly straight. All right, so that's the principle that we're using, or short pieces of curves, if you like. are nearly straight. All right, so now, so I'm going to do this by flipping it around, because it turns out that this numerator is a negative number. If I want to interpret it as a length, I'm going to want a positive quantity. So I'm going to write down 1 minus cosine theta here, and then I'm going to divide by theta there. All right? Again, I'm going to make some kind of interpretation. Now this time, I'm going to draw the same sort of bow and arrow arrangement, but maybe I'll exaggerate it a little bit. So here's the vertex of the sector, but we'll maybe make it a little longer. All right, so here it is, and here was that middle line, which was the unit. Whoops. Okay, I think I have to tilt it up. And let's try it from here. All right. Well, you know, on your pencil and paper, it'll look better than it does on my blackboard. Okay, so here we are. Here's this shape. Now, this angle is supposed to be theta, and this angle is another theta. So here we have a length, which is again theta, and another length, which is theta over here. That's the same as in the other picture, except we've exaggerated it here. And now we have this vertical line, which again I'm going to draw in green, the bowstring. But notice that as the vertex gets farther and farther away, the curved line gets closer and closer to being a vertical line. That's sort of the flip side by expansion of the zoom-in principle, the principle that the curves are nearly straight when you zoom in. If you zoom out, that would mean sending this vertex with, except we've exaggerated it here. And now we have this vertical line, which again I'm going to draw in green, the bowstring. But notice that as the vertex gets farther and farther away, the curved line gets closer and closer to being a vertical line. That's sort of the flip side by expansion of the zoom-in principle, the principle that the curves are nearly straight when you zoom in. If you zoom out, that would mean sending this vertex way out somewhere. The curved line, the piece of the circle, gets more and more straight. And now let me show you where this numerator, 1 minus cosine theta, is on this picture. So where is it? It's, well, this whole distance is 1, but the distance from the vertex to the green is cosine of theta, right? Because this is theta, so dropping down the perpendicular, this distance down back to the origin is cosine theta. So this little, and now let me show you where this numerator, 1 minus cosine theta, is somewhere. The curve, that's sort of the flip side by expansion of the zoom-in principle, the principle that the curves are nearly straight when you zoom in. If you zoom out, that would mean sending this vertex way out somewhere. The curved line, the piece of the circle, gets more and more straight. And now let me show you where this numerator, 1 minus cosine theta, is on this picture. So where is it? It's, well, this whole distance is 1, but the distance from the vertex to the green is cosine of theta, right? Because this is theta, so dropping down the perpendicular, this distance down back to the origin is cosine theta. So this little tiny segment here, which is basically the gap between the curve and the vertical segment. So the gap is equal to 1 minus cosine theta. Since from the vertex, if you zoom out, that would mean sending this vertex way out somewhere. The curved line, the piece of the circle, gets more and more straight. And now let me show you where this numerator, 1 minus cosine theta, is on this picture. So where is it? It's, well, this whole distance is 1, but the distance from the vertex to the green is cosine of theta, right? Because this is theta. So dropping down the perpendicular, this distance down back to the origin is cosine theta. So this little tiny bitty segment here, which is basically the gap between the curve and the vertical segment. So the gap is equal to 1 minus cosine theta. Right? And so now you can see that as this point gets farther away, if this got sent off to the theta center, you would hardly be able to tell the difference. The bowstring would coincide with the bow, and this little gap between the bowstring and the bow would be tending to 0. And that's the statement that this tends to 0. This theta tends to 0. The scaled version of that. Yeah, question down here.
You also tend to 0 then?
The question is, doesn't the denominator also tend to 0? And the answer is yes. In my strange analogy here with zooming in, what I did was I zoomed out the picture. So in other words, if you imagine, you're taking this and you're putting it under a microscope over here, and you're looking at something where theta is getting smaller and smaller and smaller and smaller. All right? But now, because I want my picture, I expanded my picture. So the ratio is the thing that's preserved. So if I make it so that this gap is tiny, yeah, let me say this one more time. The ratio is the thing that's preserved. So if I make it so that this gap is tiny, yeah, let me say this one more time. I'm afraid I've made life complicated for myself. If I simply let this theta tend into 0, that would be the same effect as making this closer and closer in, and then the vertical would approach. But I want to keep on blowing up the picture so that I can see the difference between the vertical and the curve. So that's very much like if you're on a video screen, you zoom in, zoom in, zoom in, zoom in. So the question is, what would that look like? That has the same effect as sending this point out farther and farther in that direction, to the left. And so I'm just trying to visualize it for you by leaving the theta at the scale, but actually the scale of the picture is then changing when I do that. So both theta is going to 0, but I'm rescaling it so that it's of a size that we can look at it and then imagining what's happening to it. Okay, does that answer your question?
My question is, that seems to prove that that limit is equal to 0 over 0.
It proves more than it's equal to 0 over 0. It's the ratio of this little shortening to this longer thing. And this is getting much, much shorter than this total length. You're absolutely right that we're comparing two quantities which are going to 0, but one of them is much smaller than the other. In the other case, we compare two quantities which are both going to 0, and they both end up being about equal in length. But here, the previous one was this green line. Here it's this little tiny bit here, and it's way shorter than the 2 theta distance. All right? Or theta. Yeah, another question.
Cos theta minus 1, or cos theta is the same as 1 minus cos theta over English.
Cos theta minus 1 over... So here, what I wrote is cosine delta x minus 1 divided by delta x. Okay? And I claim that it goes to 0. Here, I wrote the minus that. That is cosine theta. I replaced theta by delta x by theta, but then I wrote this thing. So cosine minus theta minus 1 is the negative of this. All right? And if I show that this goes to 0, it's the same as showing the other one goes to 0. Another question. Theta minus 1 is the negative of this. All right? And if I show that this goes to 0, it's the same as showing the other one goes to 0. Another question. So the question is, what about this business about arc length? So the word arc length, that shape, that orange shape is an arc. And we're just talking about the length of that arc, and so we're calling it arc length. That's what the word arc length means. It just means the length of the arc. Why is this length theta? Okay, so this is a very important point. In fact, it's the very next point that I wanted to make. Namely, notice that in this calculation, it was very important that we use length. And that means that the way that we're measuring theta is in what are known as radians. All right? So that applies to both B and A. It's a scale change in A and doesn't go in. But in D, it's very important. The only way that this orange length is comparable to this green length, the vertical is comparable to the arc, is if we measure them in terms of the same notion of length. If we measure them in degrees, for example, it would be completely wrong. We divide up the angles into 360 degrees, and that's the wrong unit of measure. The correct measure is the length along the unit circle, which is what radians are. And so this is only true. This is only true here if we use radians. All right? So again, a little warning here, that this is in radians. So now here x is in radians. And the formulas are just wrong if you use other units. Yeah. Okay, so the second question is, why is this crazy length here 1? And the reason is that what I did was, the relationship between this picture up here and this picture down here is that I'm drawing a different shape. Namely, what I'm really imagining here is a much, much smaller theta, okay? And then I'm blowing that up in scale. So this scale of this picture down here is very different from the scale of the picture up there. And if the angle is very, very, very small, then 1 has to be very, very long in order for me to finish the circle. So in other words, this length is 1 because that's what I'm insisting on. So I'm claiming that that's how I define this circle, to be a unit radius. Another question.
If I'm able to, I'm having a little bit of conceptualize it because as theta gets smaller and smaller, the ratio between 1 minus percentage and that means the difference is just 1.
Okay, so the question is, it's hard to visualize this fact here. Okay, so let me take you through a couple of steps, all right? Because I think probably other people are also having trouble with this visualization. The first part of the visualization, I'm going to try to demonstrate on this picture up here. The first part of the visualization is that I should think of the beak of a bird closing down, getting narrower and narrower. So in other words, theta has to be getting, the angle theta has to be getting smaller and smaller and smaller. Okay, that's the first step. So that's the process that we're talking about. Now, in order to draw that, once theta gets incredibly narrow, in order to depict that, I have to blow the whole picture back up in order to be able to see, otherwise it just disappears on me. In fact, in the limit, theta equals 0 is meaningless. It's just a flat line. That's the whole problem with these tricky limits, is they're meaningless right at the 0, 0 level. It's only just a little away that they're actually useful, that you get useful geometric information out of them. So we're just a little away. So that's what this picture down below in part A is meant to be meaningless right at the 0, 0 level. It's only just a little away that they're actually useful, that you get useful geometric information out of them. So we're just a little away. So that's what this picture down below in part A is meant to be. It's supposed to be that the theta is open a tiny crack, just a little bit. And the smallest I can draw it on the board for you to visualize is using the whole length of the blackboard here for that. So I've opened a little tiny bit. By the time we get to the other end of the blackboard, of course, it's fairly wide. But this angle theta is very narrow. It's a very small angle. All right, so I'm trying to imagine what happens as this collapses. Okay? Now, when I imagine that, I have to imagine a geometric interpretation of both the numerator and the denominator of this quantity here. And just see what happens. Now, I claim the numerator is this little tiny bit over here. And the denominator, vertical curve there. And I'm claiming, so this is what you have to imagine, is that as it gets smaller and smaller and smaller still, that has the same effect of this thing going way, way, way farther away, and this vertical curve getting closer and closer and closer to the green. And so that the gap between them gets tiny and goes to 0. All right? So not only does it go to 0, that's not enough for us, but it also goes to 0 faster than this theta goes to closer and closer. And that's what's over. I hope the evidence is pretty strong here because it's so tiny already at this stage. All right. It also goes to 0 faster than this theta goes to 0. And that's what's over. I hope the evidence is pretty strong here because it's so tiny already at this stage. All right. We are going to move forward, and you'll have to ponder these things some other time. So I'm going to give you an even harder thing to visualize now, so be prepared. Okay? Okay. So now, the next thing that I'd like to do is to give you a second proof, because it really is important, I think, to understand this particular fact more thoroughly, and also to get a lot of practice with sines and cosines. So I'm going to give you a geometric proof of the formula for sine here, for the derivative of sine. So here we go. This is a geometric proof of this fact. This is for all theta. Right? So far we only did it for theta equals 0. And now we're going to do it for all theta. This is a different proof, but it uses exactly the same principles. All right? So I want to do this by drawing another picture. And the picture is going to describe y, which is sine theta, which is the, if you like, the vertical position of sums going around in a circle. And so here's the circle, here's the origin. We're going to move. All right, so here it will be delta theta, position r. And then this distance here, theta's angle. And the formula for y is sine theta, so that's telling us the rate of change of sine theta. Think a little bit about the corner there. Again, one time. So here's Q, here's a piece of the arc, curve. They were all equations. One. All right, so delta y is p, y moves. So let's just. Formula for y sine theta is it here. Delta, but I wrote dq, huh? All right, that's not. All right, so delta y is PR. And now I want to draw the diagram again one time. So here's the curve here, which is a piece of the arc of the circle. But really, what I want to keep in mind is something that I did also in all these other arguments, which is, maybe I should have called about what this is. Formula for y is the point moving around in we'll start changing PR that I wrote. Here's R and here's P. What I want to keep in mind is something that I did also in all these other arguments, which is, maybe I should have called this orange, but I'm going to think of the straight line between. So it's the straight line approximation to the curve that we're always interested in. So the straight line is much simpler because then we just have a triangle here, and in fact, it's a right triangle. Right? So we have the geometry of a right triangle, which is going to now let us do all of our calculations. Okay, so now the key step is this same principle that we already used, which is that short pieces of curves are nearly straight. So that means that this piece of the circular arc here from P to Q is practically the same as the straight segment from P to Q. All right, so that's this principle that well, let's put it over here, is that PQ is practically the same as the straight segment from P to Q. So how are we going to use that? Well, we want to use that quantitatively in the following way. What we want to notice is that the distance from P to Q is approximately delta theta PQ. So how are we going to use that? Well, we want to use that quantitatively in the following way. What we want to notice is that the distance from P to Q is approximately delta theta, right? Because the arc length along that curve, the length of the curve is delta theta, so the length of the green, which is PQ, is almost delta theta. So this is essentially delta theta, this distance here. Now, the second step, which is a little trickier, is that we have to work out what this angle is. So our goal, I'm going to put it one step below because I'm going to put the geometric reasoning in between, is I need to figure out what the angle QPR is. If I can figure out what this angle is, then I'll be able to figure out what this vertical distance is, because I'll know the hypotenuse and I'll know the angle, so I'll be able to figure out what the side of the triangle is. So now, let me show you why that's possible to do. So in order to do that, first of all, I'm going to trade the boards and show you where the line PQ is. So the line PQ is here. That's the whole thing. And the key point about this line that I need you to realize is that it's practically perpendicular. It's almost perpendicular to this ray here. Right? It's not quite because the distance between P and Q is non-zero, so it isn't quite. But in the limit, it's going to be perpendicular, exactly perpendicular, the tangent line to the circle. So the key thing that I'm going to use is that PQ is almost perpendicular to OP. All right? The ray from the origin is basically perpendicular to that green line. And then the second thing I'm going to use is something that's obvious, which is that PR is vertical. Okay? So those are the two pieces of geometry that I need to see. And now notice what's happening upstairs on the picture here in the upper right. What I have is the angle theta is the angle between the horizontal and OP. That's angle theta. If I rotate it by 90 degrees, the horizontal becomes vertical, becomes PR, and the other thing rotated by 90 degrees becomes the green line. So the angle that I'm talking about, I get by taking this guy and rotating it by 90 degrees. It's the same angle. So that means that this angle here is essentially theta. That's what this angle is. Let me repeat that one more time. We started out with an angle that looks like this, which the horizontal, that's the origin, straight out horizontal, that's the thing that's labeled 1, that distance there. And then I also have that's my right arm, which is down here. My left arm is pointing up, and it's going from the origin to the point P. So here's the horizontal, and the angle between them is theta. And now, what I claim is that if I rotate by 90 degrees up, like this, without changing anything, so that was what I did, the horizontal will become a vertical. That's PR, that's going up. PR. And if I rotate OP 90 degrees, that's exactly PQ. Okay? So let me even, well, I think I will draw it on there one time. Let's see if you can, let's do it with some arrows here. So I started out with this, and then we'll label this as, let's see, label this as orange. Okay, so red to orange, and then I rotate by 90 degrees, and the red becomes this, starting from P, and the orange rotates around 90 degrees and becomes this thing here. All right? So this angle here is the same as the other one, which I just drawn. All right? Different. Or different origins for different vertices for the angles. Okay? Well, I didn't say that all arguments were supposed to be easy. All right, so I claim that the conclusion is that this angle is approximately theta. And now we can our calculation, because we have something with the hypotenuse being delta theta, and the angle being theta, and so this segment here, PR, is approximately the hypotenuse length times cosine of the angle. All right? And that is exactly what we wanted. If we divide by delta theta, we get delta y divided by delta theta is approximately cosine theta. Right? And that's the same thing as, so what we want in the limit is exactly the delta theta going to 0 delta y, where delta theta is equal to cosine theta. So we get an approximation on a scale that we can visualize, and in the limit, the formula is exact. Okay, so that is a geometric argument for the same result, namely that the derivative of sine is cosine. Yeah. You will have to do some kinds of geometric proofs sometimes. When you'll really need this is probably in 1802. So you'll need to make reasoning like this. This is, for example, the way that you actually develop the theory of arc length, and dealing with delta x's and delta y's is a common tool. All right, I have one more thing that I want to talk about today, which is some general rules. And so we took a little bit more time than I expected with this. All right, I have one more thing that I want to talk about today, which is some general rules. And so we took a little bit more time than I expected with this. So what I'm going to do is just tell you the rules, and we'll discuss them in a few days. So let me tell you the general rules. So these were the... Now, the way that you should remember this is that if you take the product of two functions and differentiate them, you get the derivative of one times the other, plus the other times the derivative of the one. Now, the way that you should remember this, and the way that I'll carry out the proof, is that you should think of it as you change one at a time. And that says the following, that you divide formula. Let me just... All right, so because we're out of time, we're not going to prove these today, but we'll prove these next time, and you're definitely going to be responsible for these kinds of proofs.
The following content Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
I'm Haynes Miller. I'm substituting for David Jarson today. So you have a substitute teacher today. So I haven't been here in this class with you, so I'm not completely sure where you are. I think you've just been talking about differentiation. And you've got some examples of differentiation, like these basic examples. The derivative of x to the n is n x to the n minus 1. And I think maybe you spent some time computing the derivative of the sine function as well recently. What do you got? The constant comes outside, like this. Or I could write cu prime is z u prime. That's this. Multiplying by a constant. And I think you also know about differentiating the sum. Or I could write this as u plus v prime is u prime plus v prime. So I'm going to be using those, but today I'll talk about a collection of other rules about how to deal with it. So let's begin by talking about the product of functions, and but cases instead of different ones like I did here. So the first function is x to the n, and the second one is sine of x, and we're going to apply this rule. Then I do it the other way. I differentiate longer ones. Well, e sub which is u of x times v of x. U right there. Let's see if we can get the rest of it in place. So the change in x is u of x plus delta x minus u of x, right? That's the change in x. It occurs, this part of it occurs up here multiplied by v of x plus delta x. So let's put that in too. Now this equality sign isn't very good right now. I've got this product here, adding in u of x, and this by, divide this by delta x. So delta uv divided by delta x is, well, I'll say delta u divided by delta x times v of x plus here. V, that uses continuity of v. So v of x plus delta x goes to, as I wrote, minus u times v, and that's just what I started with. What's left? So this v squared. This makes things on the bottom. That's what delta u is. It's the change in u, v. That's u times delta v. And I divide all this by... v plus delta v times u. Okay. Now the reason I like to do it this way is that you see the cancellation happening here. uv and uv occur twice, and so I can cancel them, and I will. analyze these questions as denominator, like delta u times v minus u times delta. So delta u, it's the new value of u. The value of u, the value of u at x plus delta x, it's u plus delta u, right? That's what delta u is. It's the change in u when x gets replaced by delta x. Cut off the old values, which are u minus v. This will be easier to work this out. Okay. Now the reason I like to do it this way is that you see the cancellation happening. UV and let's see an application. Let's see an example. So dv dx, well, v is what I'm going to take the special case where u is equal to O. We computed the derivative of 1 over x to the n, which I could also write as x to the minus n, right? So I computed the derivative of negative power. So how does that compare with the formula that we had up here? The derivative of the power of x is that power times x to 1 less than that power. That's exactly the same as the rule that I wrote down here. But the power here happens to be a negative number, and the same negative number shows up as a coefficient, and there in the exponent. So the rule, I'm applying x to the minus 2, is a value. So I talked about the product rule, and that standard rule is true for negative as well as positive exponents. Raised to the 10th power. That's a new one. Don't write sine to the 10. The method of dealing with this kind of composition of functions is to use new variable names. What I mean is, I can think of this sine of t raised to the 10th power, I can think of it as a two-step process. First of all, I compute the sine of t, and let's call the result x. There's the new variable name. And then I express y in terms of x. So y says, take this and raise it to the 10th power. In other words, y is the function x to the 10th power. And then you plug x equals sine of t into that, and you get the formula for what y is in terms of t. So it's good practice to introduce new letters when they're convenient, and this is one place where it's very convenient. So let's find a rule for differentiating a composition, a function that can be expressed by doing one function and then applying a function. And here's the rule. Well, maybe I'll actually derive this rule first, and then you'll see what it is. In fact, the rule is very simple to derive with respect to t, with respect to the original variable t. Well, because of that intermediate variable, I can write this as delta y divided by delta x times delta x divided by delta t. It cancels, right? The delta x cancels. The change in that intermediate variable cancels out. This is just basic algebra. What happens when I let delta t get small? Well, this gives me dy dt. And on the right-hand side, I get dy dx times dx dt. So students will remember this rule. This is the rule. that you can cancel out that differentiation takes of a composition is a product. It's just the product of the two derivatives. So that's how you differentiate a composite of two functions. And let's just do an example. Let's do this example. See how that comes out. Outside function. The inside function is x as a function of. Well, let's differentiate the outside function. Take dy dx. Differentiate it with respect to that variable x. In this account thing, I want to. People have a chain fence. I think I've decided that lets you burst free. Let me give you another application of the chain rule. Decided what it is. It's because by using it, you burst the chains. Sine of t. So that tells me that I get 10 times sine of t raised to the 9th power, that's x to the 9th, times the cosine of t. Or what's the same thing? Sine to the 9th of t, cosine of t. So there's an application of the chain rule. You know, people often wonder where the name chain rule comes from. I was just wondering about that myself. Is it because it chains you down? It's a chain. Is it because it chains you down? Is it like a chain fence? I think I've decided what it is. It's because by using it, you burst the chains of differentiation. You can differentiate many more functions using it. So when you want to think of the chain rule, just think of that chain rule. It lets you burst free. Let me give you another application of the chain rule. Let me give you another application of the chain rule. Ready for this one? So I'd like to differentiate the sine of 10t. Now, okay, so this is again, it's a composite of two functions. What's the inside function? Okay, so I think I'll introduce c. I take the derivative of the outside function. What do I think about? I'm not quite done yet. I haven't differentiated the inside function. The derivative of 10t is 10, so you got the same result. A little shortcut that you'll get used to. Really and truly, once you have the chain rule, the world is yours to conquer. It's because you're in a very, very powerful position. Okay, well, let's see. What have I covered today? I talked about product rule, quotient rule, composition. I should tell you something about higher derivatives as well. So let's do that. Is u. Okay, so the u prime prime is minus the cosine of x. Let's do it again. Now, after a while, you get tired of writing these things, and so maybe I'll use the notation u upper 4. That's the fourth derivative. That's u prime 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 prime, or it's u prime 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 differentiated again, fourth derivative. And what is that in this example? Okay, the cosine has derivative minus the sine, like you told me, and that minus sign cancels with that sign, and altogether I get plus the sine of x. That's pretty bizarre. When I differentiate the function sine of x 4 times, I get back to the sine of x again. That's the way it is. Now, this notation, prime 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 prime, and things like that, they're different. I think we've already here today used this capital D for the symbol ddx, the derivative. That's what I've done. So that's ddx applied to the function du dx. Differentiate the derivative. That's what I've done. Or I could write that as ddx applied to u. Just pulling that u outside. Do it to the function u. Further, and write, but that's not what's intended. This is not d of x squared. What's intended is the quantity dx squared. In this notation, which is very common, what's intended by the denominator is the quantity dx squared. It's part of this second differentiation operator. So I've written a bunch of equalities down here, and the only content to them is that these are all different notations for the same thing. You'll see this notation very commonly. And so, for instance, the third derivative is d cubed u divided by dx cubed, and so on. Sorry? Somebody's talking. Yes, absolutely. Or an equally good notation is to write the operator, capital D, done 3 times to u. Absolutely. So I guess I should also write over here when I was talking about d squared, the second derivative. Another notation is do. So the question is whether the fourth derivative always gives you the original function back, like what happened here. No, that's very, very special to sines and cosines. Right. So let's do this bit by bit. What's the first derivative of x to the n? Now, for this application, I want to take n to be 1. One comes squared to the n, and calculate what dnx to the n is. So I get the same number, n times n minus 1, and so on, times 2, and then I guess I'll say times 1.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So we're ready to begin the 5th lecture. I'm glad to be back. Thank you for entertaining my colleague, Haynes Miller. So today we're going to continue where he started. Namely, what he talked about was the chain rule, which is probably the most powerful technique for extending the kinds of functions that you can differentiate. And we're going to use the chain rule in some rather clever algebraic ways today. So the topic for today is what's known as implicit differentiation. So implicit differentiation is a technique that allows you to differentiate a lot of functions you didn't even know how to find before. And it's a technique, let's wait for a few people to sit down here. Physics, huh? Okay, well, more physics. We'll take a break. You can get those after class. Down here. Physics, huh? Okay, well, more physics. We'll take a break. You can get those after class. All right, so we're talking about implicit differentiation, and I'm going to illustrate it by several examples. So this is one of the most important and basic formulas that we've already learned part way, namely the derivative of x to a power is a times x to the a minus 1. Now, what we've got so far is the exponents 0, plus or minus 1, plus or minus 2, etc. You did the positive integer powers in the first lecture, and then yesterday, Professor Miller told you about the negative powers. So what we're going to do right now, today, is we're going to consider the exponents which are rational numbers, ratios of integers. So a is m over n, m and n are integers. All right, so that's our goal for right now, and we're going to use this method of implicit differentiation. In particular, it's important to realize that this covers m and n are integers. All right, so that's our goal. For right now, and we're going to use this method of implicit differentiation. In particular, it's important to realize that this covers the case n equals 1, and those are the nth roots. So when we take the 1 over n power, we're going to cover that right now, along with many other examples. Okay? So this is our first example. So how do we get started? Oh, we just write down a formula for the function. The function is equation to the nth power. Apply y to the n is equal to x to the m. All right, so that's just the same equation rewritten. And now, what we're going to do is we're going to differentiate. So we're going to apply dy dx to the equation. Now, why is it that we can apply it to the second equation, not the first? Equation. So maybe I should call these equations 1 and equation 2. The point is that we can apply it to equation 2. Now, the reason is that we don't know how to differentiate x to the m over n. That's something we just don't know yet. But we do know how to differentiate integer powers. Those are the things that we took care of before. So now we're in shape to be able to do the differentiation. So I'm going to write it out explicitly over here without carrying it out just yet. That's d by dx of y to the n is equal to d by dx of x to the m power. And now, you see, this expression here requires us to do something we couldn't do before yesterday. Namely, this y is a function of x. So we have to apply the chain rule here. So this is the same as, this is by the chain rule now, d by dy y to the n times dy dx. And then on the right-hand side, we get the chain rule here. So this is the same as, this is by the chain rule now, d by dy of y to the n times dy dx. And then on the right-hand side, we can just carry it out. We know the formula. It's m x to the n minus 1. All right, so this is our scheme. And now you'll see in a minute why we win with this. So first of all, there are two factors here. One of them is unknown. In fact, it's what we're looking for. But the other one is going to be a known quantity because we know how to differentiate y to the n with respect to y. That's the same formula, although the letter has been changed. And so this is the same as, I'll write it underneath here, n y to the n minus 1. dy dx is equal to m x to the n minus 1. Okay, now comes, if you like, the non-calculus part of it. Remember the non-calculus part of the problem is always the messier part of the problem. So we want to figure out this formula. This formula, the answer over here, which maybe I'll put in a box now, has this expressed much more simply, only in terms of x. And what we have to do now is to solve for dy dx using algebra and then solve it all the way in terms of x. So first of all, we solve for dy dx. So I do that by dividing the factor on the left-hand side. So I get here m x to the m minus 1 divided by n y to the n minus 1. And now I'm going to plug in, right? So now we're almost done, but unfortunately we have this mess of exponents that we have to work out. I'm going to write it one more time. So I already recognize the factor a out front. That's not going to be a problem for me, and that's what I'm aiming for here. But now I have to encode all these powers, so let's just write it out. It's m minus 1, and then it's minus the quantity n minus 1 times out front. That's not going to be a problem for me, and that's what I'm aiming for here. But now I have to encode all of these powers, so let's just write it out. It's m minus 1, and then it's minus the quantity n minus 1 times m over n. All right, so that's the law of exponents applied to this ratio here. And then we'll do the arithmetic maybe just over here in the next board. So we have here m minus 1. All right, so that's the law of exponents applied to this ratio here. And then we'll do the arithmetic maybe just over here in the next board. So we have here m minus 1 minus n minus 1 m over n is equal to m minus 1. And if I multiply n by this, I get minus m. And if the second factor is a minus minus, that's a plus, and it says a x to the a minus 1.
So the idea of giving implicit
All right, so we've done our first example here, and so now we're in shape to be able to do the, and now I'm going to write it out explicitly over here without carrying it out just yet. That's d by dx of y to the n is equal to d by dx of x to the m power. And now, you see, this expression here requires us to do something we couldn't do before yesterday, namely, this y is a function of x, so we have to apply the chain rule here. So this is the same as, this is by the
implicit differentiation.
rule now. D by dy of what we couldn't do before of y to the n means that we took applied to equation 2. Now, the reason is that here, this is the easier part of the problem. So we want to figure out this formula. This formula now comes, if you like, x is equals m. No. So I do that by, that's what I'm aiming for here, the law of 1 m over n. The two m's cancel, and I have here minus 1. Again, just a bunch of arithmetic from this point forward, from this substitution on. All right, so this equals a x to the a minus 1. Again, just a bunch of arithmetic from this point forward, from this substitution on. It's just the arithmetic of exponents. All right, so we've done our first example here, and I guess I want to give you a couple more examples, so let's just continue. Next example, I'll keep it. This, again, indeed, let's do that. So if you solve for y here, what happens is you get y squared is equal to 1 minus x squared, and y is equal to function y, is a function of x. So if you solve for y here, what happens is you get y squared is equal to 1 minus x squared, and y is equal to plus or minus the square root of 1 minus x squared. So this, if you like, is the implicit definition, and here is the explicit function y as a function of x. And now, just for my own convenience, I'm just going to take the positive branch, right? This is the function. Let's just draw it right above here. Right? It's really a circle in disguise, and I'm just going to take the top part of the circle. So we'll take that top hump here. All right, so that means I'm erasing this minus sign. I'm just taking the positive branch. Just for my convenience, I could do it just as well with a negative branch. All right, so now I've taken the solution, and I can differentiate this. So rather than using the fractional, somebody want to tell me? What? Chain rule. Yeah, that's a step in computing a derivative of a square root. And then is to rewrite them using the fractional power notation. All right, that's the first step in computing a derivative of a square root. And then the second step here is what? Somebody want to tell me? What? Chain rule. Yeah, that's good. Chain rule, that's it. So we have two things. We just start with one, and then we do something else to it. So whenever we do two things to something, we need to apply the chain rule. So I'm doing this by the sort of advance to the 1/2, whatever it is. All right, so that's the first factor that we're going to use. Rather than actually write out a variable for it and pass through as I did previously with this, I'm doing this by the sort of square root. All right, so how do we do that? Well, the first factor I claim is the derivative of this thing. So this is a half y to the minus 1/2. So I'm doing this by the sort of advanced method now because we've already graduated. You already did the chain rule last time. So what does this mean? This is an abbreviation for the derivative with respect to blah of blah to the 1/2, whatever it is. All right, so that's the first factor that we're going to use. Rather than actually write out a variable for it and pass through as I did previously with it. Y and x variable here, I'm just going to skip that step, and I'm going to let you imagine it as being a placeholder for that variable. So this variable is now parenthesis. And then I have to multiply that by the rate of change of what's inside with respect to x, and that is going to be minus 2x. All right, the derivative of 1 minus x squared is minus 2x. And now, again, we're glomming everything together here. We couldn't have done this example 2 before example 1, because we needed to know that the power rule worked, not just for a integer, but also for a equals a half. We're using the case a equals a half right here. It's 1/2 times, and this minus a half here is a minus 1. Right, so this is the case a equals 1/2, a minus 1 happens to be minus a half. Okay, so I'm putting all those things together, and within a week you have to be doing this very automatically. So we're going to do it at this speed now. You want to do it even faster, ultimately. Yes. The question is, could I have done it implicitly without the square roots? And the answer is yes. That's what I'm about to do. Okay. So this is an illustration of what's called the explicit solution. So this guy is what's called explicit, and I want to contrast it with the method that we're going to now use today. So it involves a lot of complications. It involves the chain rule, and as we'll see, it can get messier and messier. And then there's the implicit method, which I claim is easier. All right. So let's see what happens if you do it. It involves the chain rule. And as we'll see, it can get messier and messier. And then there's implicit method, which I claim is easier. All right? So let's see what happens if you do it implicitly. The implicit method involves, instead of writing the function in this relatively complicated way with the square root, it involves leaving it alone. Don't do anything to it. In this previous case, we were left with something which was complicated, say x to the 1/3 or x 1/2 or something complicated. We had to simplify it. We had an equation 1 which was more complicated. We simplified it and then differentiated it. And so that was the simpler case. Well, here the simplest thing left with something which was complicated, say instead of writing the function in this relatively complicated way with the square root, it involves leaving it alone. Don't do anything to it. In this previous case, we were left with something which was complicated, say x to the 1/3 or x to the 1/2. Complicated. We had to simplify it. We used an equation 1 which is more complicated. We simplified it and then differentiated it. So that was the simpler case. Well, here the simplest thing for us, the simplest equation for us to differentiate is the one we started with. Squares are the practically the easiest things after first powers or 0th powers to differentiate. So we're leaving it alone. This is the simplest possible form for it. And now we're going to differentiate. So what happens? So again, what's the method? Let me remind you. You're applying d by dx to the equation. So you have to differentiate the left side of the equation and differentiate the right side of the equation. So it's this. And what you get is 2x plus 2y prime is equal to what? 0. Derivative of 1 is 0. All right, so this is the chain rule again. I did it a different way. I'm trying to get you used to many different notations at once. Here, but really just two, just the prime notation and the dy dx notation. And this is what I get, all right? So now, all I have to do is solve for y prime. So that y prime, if I put the 2x on the other side, is minus 2x and then divide by 2y, which is minus x over y. All right, so let's compare our solutions. I apologize, I'm going to have to erase something to do that. So let's compare our two solutions. I'm going to put this underneath and simplify. So what was our solution over here? It was, I'm going to have to erase something to do that. So let's compare our two solutions. I'm going to put this underneath and simplify. So what was our solution over here? It was a half of 1 minus x squared to the minus a half times minus 2x. That was what we got over here. And that is the same thing if I cancel the 2's and I change it back to looking like a square root. That's the same thing as minus x divided by square root of 1 minus x squared. All right, so this is the formula for the derivative when I do it the explicit. And I'll just compare them, these two expressions here. And notice that are the same, all right? They're the same because y is equal to square root of 1 minus x squared. Yeah, question?
Bottom half of the circle.
The question is, why did the implicit method not give the bottom half of the circle? Very good question. Square root of 1 minus x squared. Yeah, question?
Bottom half of the circle.
The question is, why did the implicit method not give the bottom half of the circle? Very good question. The answer to that is that it did. I just didn't mention it. Wait, I'll explain. So suppose I'm stuck in a minus here. Okay, I would have gotten this with a difference with an extra minus sign. But then when I compared it to what was over here, I would have had to have another different minus sign over here. So actually both places would get an extra minus sign, and they would still coincide. So actually the implicit method is a little better. It doesn't even notice the between the branches. But then when I compared it to what was over there, I would have had to have another different minus sign over here. So actually both places get an extra minus sign, and they would still coincide. So actually the implicit method is a little better. It doesn't even notice the difference between the branches. It does the job both on both the top and the bottom half. Another way of saying that is that you're calculating the slopes here. So let's look at this picture. Here's a slope. Let's just take a look at a positive value of x and just check the signs to see what's happening. If you take a positive value of x over here, x is positive, denominator is positive, the slope is negative, you can see that it's tilting down. All right? So it's okay. Now, on the bottom side, it's going to be tilting up. And similarly, what's happening up here is that both x and y are positive, and this x and this y are positive, and the slope is negative. On the other hand, on the bottom side, x is still positive, but y is negative, and it's tilting up because the denominator is negative, the numerator is positive, and this minus sign makes it a positive slope. And this x and this y are positive, and the slope is negative. On the other hand, on the bottom side, x is still positive, but y is negative, and it's tilting up because the denominator is negative, the numerator is positive, and this minus sign makes it a positive slope. So it matches perfectly in every category. So this is complicated, however, and it's easier just to keep track of one branch at a time, even in advanced math. Okay? So we only do it one branch at a time. Other questions? Okay, so now, I want to give you a slightly more complicated example here. And indeed, some of the... So here's a little more complicated example. It's not going to be... most complicated example, but, it'll be a little bit tricky, okay? So this example, I'm going to give you a fourth order equation. So y to the fourth plus xy squared minus 2 is equal to 0. Right? Now, just so happens that there's a trick to solving this equation. So actually, you can do both the explicit method and the non-explicit method. Okay, so the explicit method would say, okay, well, I want to solve for this, so I'm going to use the quadratic formula, but on y squared. This is quadratic in y squared, because there's a fourth power and a second power, and the first and the third powers are missing. So this is y squared is equal to minus x plus or minus the square root of x squared minus 4 times minus 2 divided by 2. Okay, so this x is the b, this minus 2 is the c, and a is equal to 1 in the quadratic formula. And so the formula y is plus or minus the square root of minus x plus or minus the square root of x squared plus 8 divided by 2. All right? So now you can see this problem of branches. This happens actually in a lot of cases. Coming up in an elaborate way, you have two choices for the sign here, you have two choices for the sign here. Conceivably, there's as many as 4 roots to this equation because it's a 4th degree equation. It's quite a mess. You should have to check each branch separately. And this really is that level of complexity. And in general, it's very difficult to figure out the formulas for quartic equations. But fortunately, we're never going to use them, as we're never going to need those formulas. So the implicit method is far easier. The implicit method just says, okay, I'll leave the equation in its simplest form, and now differentiate. So when I differentiate, I get 4y cubed y prime plus, now here I have to apply the product rule. So I differentiate the x and the y squared separately. First I differentiate with respect to x, so I get y squared. Then I differentiate with respect to the other factor, the y squared factor, and I get x times 2y y prime. And then the 0 gives me 0, so minus 0. All right, so there's the implicit differentiation step. I'm going to put the y squared on the other side, y. So that's so the question is, for the y, would we have to put in what we solved for in the implicit equation? And the answer is absolutely yes. That's exactly the point. So this is not a complete solution to a problem. We started with an implicit equation, we differentiated, and we got, in the end, also an implicit equation. It doesn't tell us what y is a function of x. We have to go back to this formula to get the formula for x. So for example, well, let me give you an example here. So this is the hides a degree of complexity of the problem, but it's a degree of complexity that we must live with here. So for example, at x equals 1, you can see that y equals 1 solves. That happens to be, solves y to the 4th plus xy squared minus 2 is equal to 0. That's why I picked the 2 actually, so it would be 1 plus 1 minus 2 equals 0. I just wanted to have a convenient solution there to pull out of my hat at this point. So I did that, and so we now know that when x equals 1, y equals 1, so at 1, 1 along the curve, the slope is equal to what? Well, I have to plug in here, minus 1 squared divided by 4 times 1 cubed plus 2 times 1 times 1. That's just plugging in that formula over there, which turns out to be minus 1/6. All right, so I can... On the other hand, but at just plugging in that formula over there, which turns out to be minus 1/6. So I can get it. On the other hand, but at, say, x equals 2, we're stuck using this formula star here to find y. Okay? Now, so let me just make 2 points about this, which are just philosophical points for you right now. The first is, when I promised you at the beginning of this class that we were going to be able to differentiate any function you know, I meant it very literally. What I meant is, if you know the function, we'll be able to give a formula for the derivative. If you don't know how to find a function, you'll have a lot of trouble finding the derivative. So we didn't make any promises that if you can't find a function, you will be able to find the derivative by the magic. That will never happen. And however complex the function is, a root of a 4th degree polynomial is can be a pretty complicated function of the coefficients. We're stuck with this degree of complexity in the problem. But the big advantage of this method, notice, is that although we've had to find star, we had to find this formula star, and there are many other for doing these things numerically, by the way, which we'll learn later. So there's a good method for doing it numerically. Although we had to find star, we never had to differentiate it. We had a fast way of getting the slope. So we needed to know what x and y were, but y prime we got by an algebraic formula in terms of the values here. So this is very fast for getting the slope, once you know the point. Yes. What's in the parentheses? Sorry, this is, let's see if I can manage. Is this little, is this the parentheses you're talking about? Say. Oh, this says say. Well, so maybe I should put commas around. See, sorry, this is, let's see if I can manage. Is this little, is this the parentheses you're talking about? Say. Oh, this says say. Yes. What's in the parentheses? Sorry, this is, let's see if I can manage. Is this little, is this the parentheses you're talking about? Say. Oh, this says say. Well, so maybe I should put commas around it. It was S-A-Y, comma, comma. Okay? Well, here was at x equals 1. And here's but at, say, I'm just throwing out a value here. Any other value. Actually, there is one value, my favorite value. Well, this is easy to evaluate, right? X equals 0. I can do it there. That's maybe the only one, which is, the others are a nuisance. Okay. All right. Other questions? Okay, now we have to do something more here. So I claimed to you that we could differentiate all the functions we know, but really we can learn a tremendous about some functions which are really hard to get at. So this implicit differentiation method has one very, very important application.
Implicit.
To finding inverse functions, or finding derivatives of inverse functions. So let's talk about that next. So first, maybe we'll just illustrate by an example. If you have the function y is equal to square root x for x positive, then, of course, this idea is that we should simplify this equation, and we should square it. So we get this somewhat simpler equation here. And then we have a notation for this. If we call f of x equal to square root of x, and g of y is equal to x, this is the reversal of this, then the formula for g of y is that it should be y squared. And in general, if we start with any old y is equal to f of x, and we just write down, this is the defining relation for function g, the property that we're saying is that g of f of x has got to bring us back to x. And we write that in a couple of different ways. We call g the inverse of the defining relation for function g. The property that we're saying is that g of f of x has got to bring us back to x. And we write that in a couple of different ways. We call g the inverse of f, and also we call f the inverse of g. Although I'm going to be silent about which variable I use because people mix them up a little bit, as we'll be doing when we draw a few pictures of this. So let's draw a picture of both f and f inverse on the same graph. That's some shape like this. And now, in order to understand what g of y is, so let's do the analysis in general, but then we'll draw it in this particular case. If you have g of y is equal to x. That's really just the same equation, right? This is the equation g of y is equal to x. That's y squared equals x. This is y equals square root of x. Those are the same equation. It's the same curve. But suppose now that we wanted to write down what g of x is. Okay, in other words, we wanted to switch the variables, so draw them, as I said, on the same graph with the same x and the same y axes. Then we wanted to write down what g of x is. Okay. We wanted to switch the variables, so draw them, as I said, on the same graph with the same x and the same y axes. Then that would be, in effect, trading the roles of x and y. We have to rename every point on the graph, which is the ordered pair x, y, and trade it for the opposite one. And when you exchange x and y, so to do this, exchange x and y. And when you do that, on the graphically, what that looks like is the following. Suppose you have a place here, and this is the x, and this is the y. Then you want to trade them, so you want the y here diagonal. Right? So this guy here is y equals f. Right? They're just, if you take this one and you turn it, you reverse the roles of the x-axis and the y-axis, tilt it on its side. All right, so that's a picture of what an inverse function is. Just to say it in general, the derivative of any inverse function, provided
Why? Because the inverse function is contained.
we know the derivative of the function. Right? So let's do that for what is an example which is truly complicated and a little subtle here and has a very pretty answer. So we'll carry out an example here, which is the function y is equal to the inverse tangent. So again, for and y, then we'll do the computation. So is this one? So that's the function tan x. Okay, and so the one that we have to sketch is this one which we get by reflecting this across the axis. All right, so that's going to be, well, not the axis, sorry, the diagonal. All right, this slope, by the way, should be less, so a little lower here, so that you can have it going down and up. All right, so let me show you what it looks like. So on the front end, it's going to look a lot like this one. So this one. It's curved down, and so the reflection across the diagonal curved up. Here, this is curving up, so the reflection is going to curve down. It's going to look like this. All right, maybe I should, sorry, let's use a different color because it's reversed from what we had before. So I'll just call it green. All right, we'll do this. All right, now, the original curve in the first quadrant eventually had an asymptote which was straight up. So this one is going to have an asymptote which is horizontal, and that level is what? What's the highest? Right there. This is pi over 2 up here. All right, now similarly the other way, we're going to do this. And this bottom level is going to be minus pi over 2. So there's the picture of this function. It's defined for all x. So this green guy is y equals tan. The limit notation is x goes to infinity, let's say, tan inverse x is equal to pi over 2. That's an example of one value of interest in addition to the finite values. Okay, so the first ingredient that we're going to need is we're going to need the derivative of a tangent function. So I'm going to recall for you, and you maybe haven't worked this out yet, but I hope that many of you have, that if you take the derivative with respect to y of tan y, so this you do by the quotient rule, or if you like, 1 over cosine squared y times, in the other notation, y prime is equal to 1. All right. Okay, so we need that ingredient, and now we're just going to differentiate our equation. And what do we get? We get, again, d by dy, tan y, times dy dx is equal to 1. Or if you like, 1 over cosine squared y times, in the other notation, y prime is equal to 1. So I just used the formula that I just wrote down there. All right, now all I have to do is solve for y prime. It's cosine squared y. Okay? Unfortunately, this is not the form that we ever want to leave these things in. Again, this is the same problem we had with that ugly square root expression or with any of the others. We want to rewrite it in terms of x. Our original question was, what is d by dx of tan inverse of x? Now, so far, we have the following answer to that question. It's cosine squared of tan inverse x. Okay? Now, this is a correct answer, but way too complicated. Now, this is, or if you like, 1 over cosine squared y. Now, all I have to do is solve for y prime expression, or with cosine squared, this occasion it comes out to be cosine squared y. Yeah, 1 over cosine squared. You can recognize the cosine squared from the fact that you should get v squared in the denominator, and somehow the numerator all cancels and simplifies to 1. Okay? And this is also known as secant squared y. All right? So that's something that, if you haven't done it yet, you're going to have to do this as an exercise. All right. Okay, so we need that ingredient, and now we're just going to differentiate our equation. And what do we get? We get, again, d by dy, tan y, times dy dx is equal to 1. Or if you like, 1 over cosine squared y times, in the other notation, y prime is equal to 1. So I just used the formula that I just wrote down. All right, now all I have to do is solve for y prime. It's cosine squared y. Okay? Unfortunately, this is not the form that we ever want to leave these things in. Again, this is the same problem we had with that ugly square root expression or with any of the others. We want to rewrite it in terms of x. Our original question was, what is d by dx of tan inverse of x? Now, so far, we have the following answer to that question. It's cosine squared of tan inverse x. Okay? Now, this is a correct answer, but way too complicated. Now, that doesn't mean that if you took a random collection of functions, you wouldn't end up with something that's complicated. But these particular functions, these beautiful circular functions involved with trigonometry, all have very nice formulas associated with it. And this simplifies tremendously. And so one of the skills that you need to do to develop when you're dealing with trig functions is to simplify this. And so let's see now that expressions like this all simplify. So here we go. There's only one formula, one ingredient that we need to use to do this, and then we're going to draw a diagram. So the ingredient, again, is the original defining relationship that tan y is equal to x. So tan y equals x can be encoded in a right triangle in the following way. Here's the right triangle, and tan y means that y should be represented as an angle. And then its tangent is the ratio of this vertical to this horizontal side, so in the following way. Here's the right triangle, and tan y means that y should be represented as an angle. And then its tangent is the ratio of this vertical to this horizontal side, so I'm just going to pick two values that work, namely x and 1. Those are the simplest ones. So I've encoded this equation in this picture. And now, all I have to do is figure out what the cosine of y is in this right triangle here. In order to do that, I need to figure out what the hypotenuse is. But that's just the square root of 1 plus x squared. And now I can read off what the cosine of y is. So the cosine of y is 1 divided by the hypotenuse. So it's 1 over square root, 1 plus x squared. Okay? And so cosine squared is just 1 over 1 plus x squared. And so our answer over here, the preferred answer,
1.
So what I'm going to do is I'm going to subtract log of 1 from it. That's just equal to 0, right? So this is not a problem. And I'll put some parentheses around this. Right now, you're supposed to recognize all of a sudden what this thing, okay, so we got it. We got the limit. And now we just have to work backwards to figure out what this limit that we got over here is. So let's do that. So let's see here. The log approach 1. So the limit, as n goes to infinity, of 1 plus 1 over n to the n. So sorry, the log of this. Yeah, let's write it this way. So this is the same thing as, well, the thing that we know is the log of this, right? 1 plus 1 over n to the n. N goes to infinity. That's the one that we just figured out. But now this thing is the exponential of that. So it's really e to this power. Yeah. So this guy is the same as the limit of the log of the limit of this thing. So I claim that with this step, we've actually closed the loop finally, because we have an honest numerical way to calculate e. Of course, there are many such, but this one is a So I claim that with this step, we've actually closed the loop finally, because we have for which we have practical methods to calculate. Okay, so see you next time.
Oke, selesai. Wow, kita sudah live 4 jam. Perasaan 3 jam. Kok 4 jam? Sudahlah. Sangat interesting. Di akhir-akhirnya sih. Lebih ke pembuktian tentang natural log ataupun ln dan number of nomor e. Sangat unik penjelasannya dan tentang konsep derivatif terhadap derivatif atau turunan terhadap fungsi-fungsi eksponensial. Jadi sangat berbeda perspektifnya, makanya mungkin agak sedikit lama, tapi ya pretty glad akan hari ini. Semoga bisa bangun lebih cepat dan kita mulai besok. Aku rencananya sih masih matematika dan coba ngerjain problem set. Besok kita coba ngerjain coba lihat lecture yang kedua dulu. Ini bab pertama tentang derivatif. Yang kedua kalau nggak salah ada integral ya, kurang tahu juga sih. Itu babnya ada 9 lecture, 9 entah 5 9 entah 7. Jadi pertama besok lihat itu, dan kita akan ngerjain problem setnya besok juga. Dan sebenarnya ada satu exam besok, tapi nggak tahu bisa terkejar apa nggak. Tapi utamakan dulu adalah problem setnya. So yeah, goodbye then.